Now we're going to look at this particular topic, sometimes it's called the future value, finding the future value. But what I'm hoping you see is that no matter the situation, you recognize that you have to use a certain formula, and then you write what you know, and then act from that point forward. Okay, so let's see. So if you're in financial class, for example, we'll have like 12 formulas for different situations, and then you start realizing if you take an algebra, if you're familiar with algebra, then that starts to boil down to not 12. They're just one, sometimes it's just solved for another one, or they're connected in some way, shape, or form. You want $20,000 in an account that earns 2.3% yearly interest. Okay, so now that means that T is in years. Compounded weekly. Okay, it's a yearly interest compounded weekly, so N is at 52. You want 20,000 in 9 years. Okay, so 9 years, I want $20,000. How much from now? 9 years from now, how much do you need to invest? And again, this is called the future value, like meaning that's what I want. What should I do now? So again, I'm gonna first write the formula. This is what I don't know. So it's called P here. I call it in the formula. Okay, don't get too hung up with the numbers or the letters here. And 2.03, and this is going to be compounded 52 times in a year, 52, and then T is in year. Okay, there's my equation. So now what do I want? How much do you need to invest if I want $20,000 9 years from now? So now I want this number to be 20,000. What I don't know is that P, and when should this happen? Should happen 9 years from that starting position. So now I need to solve this. But if you look carefully, this is not exponential anymore. This is a constant. That whole thing is a constant. As a matter of fact, if this is just a constant, then this is just a number. So I have a number times P equals 20,000. So what kind of equation is this? This is just linear. That's all. It's just a linear equation. Wow, that's pretty simple, right? So how do I solve this? Well, I'm going to just take and divide both sides by this constant. So I think 20,000 divided by 1 plus 0.023 52 2 to the 9th power. And now it's just a matter of putting all this, and this is approximately P. Well, this is exactly P. Now I'm going to approximate this. So here and enter this whole thing. Clear this. 20,000 divide by, in parentheses, 1 plus 0.023, divide that by 52, close it, and now raise the, I'm hitting the caret here to raise it. And I'm gonna raise it again because there's two numbers. I need to put parentheses here. 52 times 9, close it. Enter. And it looks like I need to run to the nearest penny. What I need is $16,261.14 rounded. Okay, that's how much I need to invest. Okay, let's do another one. Okay. Let's see. A population of town decreases by half every 10 years. Okay. What was the population 15 years ago if it is currently at 50,000? Okay. A lot of things going on. So what I like to do, just like I did here, I just write out what I know. Here's my formula. So the question now again before is like, okay, how does this town decrease? If I have it 10 years, I'm gonna, again, let's make an assumption since we're doing exponents, it's gonna be exponentially. There's many ways you can, I mean, you can decrease linearly, you can decrease by other means, but since we're in exponential form, I don't know, section, I'm gonna assume that it's decreasing exponentially. Let's make that the case. All right, so now I'm gonna write the following. I'm gonna keep this nice and simple. The amount is just gonna equal to, I don't know the current, uh, okay, so I don't know the original amount. So I'm gonna write this down. And I know that it reaches by half every 10 years. So I can only do this, right? I can only apply half of this amount every 10 years. So if t also is in years, t will be in year, t is in years, because that's what information I do have. I can apply this every 10 years. So again, notice again when I write this is that when t equals 10, all of a sudden 10 times 1/10 is 1, and that's the first time I get to use half that amount. Okay, so there's my formula. Okay, what was the population 15 years ago if it is currently at 50,000? So now we're currently at 50,000. I don't know what this is, but it's 50,000 after having gone through 15 years. So now the t here is 15. Again, what I recognize is that this is a constant, it's a linear equation. So this is what I don't know. I just need to divide both sides by this amount. So it's going to be 15 years, right? 15 divided by 10. Okay. Or 1.5. And that will give me this amount. So let's just go in a calculator and figure out what this is. So 50,000 divided by, so I'm going to put it in decimal form, 0.5, because they're exact. I can do this exact. And 15 divided by 10 is 1.5. So again, to the nearest person, so I want to round to the nearest person. This is 14,140. No, 2, 1, hang on. Nope, 141,000. Yeah, it's currently at 30,000. Okay, never mind. 141,421. Yep, 121 people. So that's rounded. So that's my original. People. These are people. Great. Now let me do it one more time. But this time I'm going to use a different model, just for fun. So I'm going to use a continuous model. All right. So what do I know if I'm going to use a continuous model? Um, Well, let's see. I'm going to first write the model down. So we have that in front of us so you can see what this is. Here's the formula. I don't know what K is, but here's what I do know. And so this is the problem. With this one, I just don't know what K is. I know, though, that I will reach half of the original amount, half of this. So, and again, we know the original amount doesn't really matter. When? Well, it's going to be in, is it 15 years? Yep. I will reach, so I don't know what the original amount, but I'll reach it 15 years from now. Okay. Okay, great. Great, 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 great. Um, oh, no, no, no. Sorry, sorry. It's half. sorry. Knew something was wrong. I get to get half every 10 years, so this should be 10. In 10 years, I'll get the half. Okay, perfect. Now I'm back with it. So I need to figure out what K is, because I need this for this formula. So I'm going to take natural log of both sides. And here I get natural log of 1/2. Here I'm going to get 10K. Fantastic, fantastic. And divide by 10. So here's what K is. Great. I found what K is. Now I'm ready to the question. What was the population 15 years ago if it is currently at 50,000? So now I know what K is, so I can put it here and apply the formula just like I did a minute ago. Okay. So if I do this, let's see. I'm at 50, so back over here, I'm working over here, 50,000 people. I don't know what this amount is, just like before. I got E, and I'm going to leave this monstrosity's natural log of 0.5, divide this by 10. But I get to reach 50,000 when I reach 15 years. So T here in the final formula will be 15. And notice there's curious elements. Notice there's a 15 to 10, 15 to 10, just like before. So if you're wondering again, does that really make sense? Yeah, look, it's right here again. So what's happening is I need this part here because it's a continuous compounding, so to speak. So, but again, this is linear. This whole thing is linear, just like before. There's just a big old constant, divide both sides by this e to the whatever. And I got 50,000 e natural log of 0.5 over 10 times 15. And this will give me what the original population is, which approximately, oops, sorry, I need to come over here, which again, approximately, let's see what this is. So enter 50,000, divide that by, this time I'm going to put E, raised to, and then it's raised to kind of quite the mess here, natural log of 0.5. And then I'm going to go this times, no parentheses, 15, well, actually, 15 divided by 10 is 1.5, so let's just go times 1.5. Let's just get to the chase. It's exact. Okay, and then close it one more time. Okay, so I entered that over. Okay, I'm happy. And again, when I do that, you'll notice that the answer is A naught is approximately, again, people. So the answer hasn't changed because, again, round it to the nearest person, whether you compound continuously or not, it won't matter. It matters if it's money a little bit, millions of dollars, but if it's some kind of radioactive material, it doesn't matter. But people, no, not gonna matter.